here, okay. So I'm going to start recording here. Okay, so you may recall from this morning that we had built this model which simulated infection spread, but where we recognized that a given realization of this simulation could be different from each other. So when we ran this, so different realizations could exhibit somewhat different results. When we ran a particular run of the model, running it at full tilt with this button here, we noted that there was a certain pattern induced, but that pattern differed in its details from run to run. For example, on this one, has various ups and downs at points in time. It goes up just before time 1,000 to about 55. If we were to run that again, bearing in mind that we have a random seed selected, we might run it another realization, and we would find many similar features in terms of the overall range of variation, in terms of the sort of qualitative or phenomenological character of what's being observed, but all different in its details. This one shot way up before 1,000. So the natural question was, what things here, which of these are regularities we can count on, which of them are flukes of a particular run? So in order to investigate that, we created this parameter variation experiment, which ran the underlying simulation model, ran main, many times. And I actually told it here to run it 100 times over. And for each such time, it accumulated data from that run here into the internal data structures in the experiment. And having done so, we have a summary over those many runs associated with the experiment results. Now, what's notable when we ran this the first time there was that we weren't modifying any parameters here, okay, for the very, very first such run. So we had this in free-form mode, and we ran it 100 times. All these parameters had precisely fixed values, but there were differences elicited between those runs. And this parameter variation experiment, and particularly this 2D histogram, provided us a way of summarizing those, summarizing across many, many runs results. And it let us recognize kind of degree of variation, and it let us recognize certain regularities between different runs that were to be expected, such as these pronounced, these marked oscillations at first. You notice there are exceptions. This is an anomalous one, a slight anomalous one, where it goes down to 0 here. It actually dies out at this low point. But for the most part, we have this oscillation down, up, and so on. And then it starts becoming a lot less regular after about time 100 to 150. So we were able to recognize that. But the important thing here, a key point, is that this came about by running the model again and again and again with no differences in the parameter. So let me ask this. Why was there any degree of variability between what we got from different runs? What was the underlying difference between the results in those runs? It was due to what? Stochastics, randomness over time, and the vagaries of who sent a message to whom, who was the initial person infected, at exactly what time did they recover from infection. Within our model, we have, within this single model, we have a set of processes that are characterized stochastically. For example, the timing of this recovery. To figure out when they recover, we draw from an exponential distribution, because this is with a fixed hazard. We draw how long they're going to be there. Maybe in some runs, that initial person infected stayed infectious longer and they infected more people. In other times, perhaps key people in the network in terms of connectivity got infected later or got infected earlier, and that made all the difference in terms of the differences. But it's not like in terms of the difference in results. But what we see here is a mixture of order and randomness. Randomness here, order here. Tapping into the existence of these stochastics, recognizing them, dignifying them, capturing them explicitly, helps us understand which things are more subject to variation and uncertainty, and which things are regular to a degree we can largely count on. And that's significant. We can also get a sense of the degree of variability in results in a way that might help us interpret empirical data. For example, we have used models like this before as thinking tools to help us explain whether variability we see in data is largely resulting from statistical effects that interact with the nature of the data, such as its 5-year age-specific rates, and therefore there's kind of aging in and aging out of cohorts, or whether it's likely due to some underlying secular changes in risk factors or what have you. So representing stochastics in models has advantages for interpreting data, for interpreting which areas of results are things we can count on and which are flukes. But it also has responsibilities associated with it. We want to run a model many times over to secure reliable results. Now, I noted that while these results were with respect to a single realization, we could also use the parameter variation experiment to run many runs with different assumptions about parameters. And I made these comments in just the closing minutes before the break, before the lunch. And I just want to emphasize that key point because it's not a minor point. One of the big advantages of the parameter variation experiment, as you might expect, is that we can perform variation of parameters. So we can say, not in a free-form mode, but in varied and range, where it will not pay attention to this number of runs, but rather deduce them from here, we could vary certain parameter assumptions. So, for example, we could vary the mean time until waning of immunity, from 10 days to 100 days by a factor of 2. Or we could examine the impacts of making that fixed and varying instead the mean recovery time, varying it from 5 days to 15 days with a step of 1. By running something like this, we can get a sense of how much model results change over that span of possible assumptions. So we can run it here, and we will see successive values associated with that mean recovery time. As it grows larger, you go from very low levels of infection, where it essentially dies out because people recover quick enough to not transmit it much at all, to much higher values as it rises. Now, you may note here that for each, so this is varying the assumptions, ladies and gentlemen, about the parameters, okay? So what we're doing here is we are varying this parameter here over this range. We could do so with 2 parameters at the same time. We could examine this over its range and consider a a Cartesian product of all, as we say. All values of this by all values of that. Readily doable. You could do 3, 4. You get a cursive dimensionality effect that at some point might motivate you to a more sophisticated scheme. One such scheme, which is readily achievable, and any number of TAs associated with this boot camp could help you, is if you want to use a sophisticated scheme, there are schemes out there, orthogonal arrays, Latin hypercubes, etc. You could readily use them here. They're not built in, but what you can do is use external tools to produce a Latin hypercube of experiments. And then you encode it in a database or you encode it in a lookup table. And what you iterate through is with a parameter, which row of that database or lookup table are what you're going to use. And based on that iteration, you assign the values for the other parameters. It's quite readily done. And again, students could help you if you want to explore that. A more sophisticated scheme than doing all, multi-way sensitivity analysis in a brute force sort of way. But for small numbers of parameters, that's readily doable. Ladies and gentlemen, sensitivity analysis is one of these processes that if you don't do it for a dynamic modeling paper you submit, it will very often lead to a dismissal of that paper as insufficiently close investigation. You really need to do sensitivity analysis for reviewers, but more significantly and more importantly, you need to do it to build your understanding some of the system and how much of a difference certain assumptions make in terms of the degree to which they change outcomes. We'll often do sensitivity analysis not over broad ranges, but sensitivity analysis around certain points. Maybe examining 10% higher, 10% lower than the original value. Or in freeform mode, you could do something like, and I'll change these back to fixed. In freeform mode, I could draw these from a distribution. So I could do something like draw the mean recovery time from a truncated normal distribution or from a log normal distribution by typing an appropriate expression here. I want to warn you against one thing, because if I don't, it's slightly atopical, but if I don't warn you now, you may discover it only rudely. There's one point of great objection I have to any logic support of statistical functions. One point that if it doesn't make my skin crawl, at least it bothers me greatly because it can pose great risk of errors. So ladies and gentlemen, for the most part, in any logic, when we have the option of using statistical distributions, we have admirable support of a wide variety of distributions. The issue is with a particular one that's most common, a normal distribution, which we might well use to in order to draw the value of a parameter during Monte Carlo analysis, running it again and again. If I wanted to draw a value from this distribution, you need to realize that the order of the parameters is different from every other package I've ever used statistically. Specifically, it requires you to specify sigma before the mu, sigma before the mean, the standard deviation before the mean, which is, again, it's opposite every convention I've ever encountered, and it's opposite my intuition. So just be aware that if you use this probability distribution picker and you insert it with that, it will know that to do that. But if you do it on your own, you have to remember to do that. But the point here, apologies for that side expression, is just a figure I need to warn you. But here, if you want to draw values from a distribution, you just draw them. We could say that this is drawn from a uniform distribution between, uniform between 1.0 and 5.0 or something like that. And we could then run 100 iterations of Monte Carlo analysis to see the results of the induced uncertainty. Now, to further sort of round out this discussion, I will note that when you do a variation in range over some ranges, one-way, multi-way, or even when you're conducting Monte Carlo analysis, you're drawing the value of each parameter from a distribution. Sometimes the question comes up, now wait a minute, now I'm changing the values of each parameter. Don't I also want to run multiple realizations per set of parameter values, per vector of parameter values, to capture the effects of stochastics on top of that? And sometimes we do. Sometimes that's something we do want to do. We don't want to just run each combination of parameters once. We want to run it 10 times, 100 times. AnyLogic provides support for that through what are called replications. And by saying we can use replications, we can say how many times do we want to run it for a given combination of parameter values. So for a specific assignment to the different parameter values involved for this model, for a specific value of these, what particular number of realizations do I want to run? And you can find me discussing it online, but there's also, you can specify a fixed number, or you could use some statistical criteria to stop based on the statistics associated with mean, taking the mean, the sample mean. Okay? So just be aware that parameter variations experiments provide a lot of options. They're very powerful, and they require quite a bit of computation, but it can be done with a minimum of fuss, and it does take advantage of parallel computation because it's, as we say, embarrassingly parallel. It can be done, many different assumptions about the parameters can be run at the same time. This is the essential aspect of it that you have seen. Okay, so I am going to be turning the floor over here in just a moment to my students, who will be walking you through a further exercise with this model. An exercise that will involve collecting additional statistics. And I want to ask them one question, because I promised them that I'd do everything up to a certain point. There's one thing I didn't do, and I want to ask Aiden and Alan, do you want me to do it? The first histogram of income, I actually did not build. Do you want me to do it with them? You can do it? It's static, yeah, great. Okay, so that was a glimpse at that model. Parameter variation captures sensitivity analysis and analyzing model results in response to stochastics, a very important part of our modeling. And it decouples the experiment from main in the sense that now experiments can run main many, many times. This next discussion will focus on a very practical need that often comes up with these models. To be able to have the requisite ability to gather the information from the model, which could then be compared to comparable empirical information from the world. How do we gather from the model cross-sectional statistics at an individual level, or statistics associated with a longitudinal evolution of individuals? How do we capture longitudinal aggregate statistics or cross-sectional? How do we record what I call flow statistics? Things like incidence, the number of people that have gotten infected in the past week, or history information, like the number of times this individual has quit smoking over their life course, or the number of pack years that they've smoked. For that discussion, I turn you to the able hands of two of my students, Auden Tehui and Alan McLean. Thanks very much.